So we are discussing the ferroelectric properties of materials, and in the last class we have discussed so far the properties of piezo and pyroelectric crystals. So as a note to this, I just go on the characteristic features of ferroelectric materials. So the ferroelectric materials are characterized by a finite electric polarization in absence of an external electric field. Obviously, this external electric field is periodic in nature, and furthermore, this polarization must possess at least two stable states and must have the ability to be reversibility switched from one state to another by the application of an electric field. So thus, the regions with different orientations of the polarization vector may coexist within a ferroelectric sample and are called the ferroelectric domains. So experimentally, the ability to switch from one state to another can be observed by an indirect measurement of the polarization as a function of an applied electric field and takes the form of a signature of the hysteresis loop. So these are the typical hysteresis loop of exhibited by the ferroelectric materials. And starting from the origin, when P equals to 0, while electric field is also 0, the possible macroscopically, if the sample has multiple domains compensating each other, the ramping up the field, the total polarization gradually increases towards a saturation value corresponding to all unit cells coherently oriented with the field. So upon further increasing the field, the polarization is further enhanced by dielectric charging. When the field is decreased back to 0 in the reverse direction, the total polarization decreases a little but remains finite, and the polarization value reached at E equals to 0 is called the remanent polarization, that is the plus PR. When the field is increased in the opposite direction, the polarization state switches suddenly for a specific field intensity called the coercive field, that is minus EC. Upon the further increase, the polarization saturates and a simple dielectric response is reached again. So in this behavior, right? So generally the same behavior is observed when the electric field is reversed, and repeated cycling results in a symmetric hysteresis loop with switching events at plus EC and minus EC. So in the presence of the internal fields, that is due to the charge accumulation in a ferroelectric transistor, the hysteresis loop may, however, be offset with respect to E equals to 0, a phenomena known as imprint. The spontaneous polarization plus PS and minus PS is usually defined as the extrapolation at 0 field of the polarization value at high fields, where the slight decrease is due to charging. So in reality, this saturation polarization PS is often higher in polycrystalline materials due to, for instance, to the formation of the opposite domains during the ramping of the field to 0, but very can be very close to as in the case of the single crystals. Although in physical sense, this hysteresis loops behaves like this elliptical behavior and the loop area is very large, but in practical sense, when we go on experimenting the materials which exhibit the ferroelectric behaviors like liquid crystals, polymers, and polycrystalline samples, these PE hysteresis loops looks like this, and the loop area is very narrow. So unlike this larger loop area, this type of very low loop area kind of behavior of P hysteresis loops, and furthermore, the saturation polarization not very uh, saturated in like this manner, it can go in a straight way and then reverse back to the opposite direction. So this is a very, uh, I would say, disparity with respect to the physical sense or the theoretical sense that we have observed in theoretical understanding. So quickly go on to the next slide. Okay, this has already been discussed that the ferroelectricity arises from the polarization catastrophe as well as the frequency of longitudinal as well as the transverse uh, frequency. So these are the important facts which I would discuss in this behavior, where all kind of ferroelectrics are the subset of pyroelectrics. The pyroelectrics are the subset of piezoelectrics, and finally all these materials are a class of dielectric materials. So another more important and astonishing thing is that at high temperatures, most ferroelectric materials exist in a paraelectric and generally centrosymmetric phase and exhibit a simple dielectric response to applied electric fields. And as I have mentioned, among the 32 crystallographic point groups, which classify crystal structures based on their symmetry, 21 are non-centrosymmetric. A necessary criteria to fulfill the above requirements. Okay, this kind of classifications are there. 21 are non-centrosymmetric, a necessary criteria to fulfill the above requirements. And in 20 of these 21 non-centrosymmetric groups, this lack of inversion symmetry is at the origin of piezoelectricity, the appearance of an electric polarization as a consequence of mechanical stress. The piezoelectric coefficient is a linear coupling between the polarization and the stress field, like this manner. If Pi is the polarization, then Dijk is the polar piezoelectric coefficient, and this is the stress. So the piezoelectric effect is a linear coupling between the polarization and the stress field, where P is the polarization vector, D is the piezoelectric tensor, this is the piezoelectric tensor, and sigma is the stress tensor. The piezoelectric tensor is specific to the material with the non uh, zero elements dependent on the crystal symmetry, thus restricting the possible polarization vector directions. By energy conservation, the same tensor can describe the inverse piezoelectric effect, coupling and strain of the materials to the external electric field is epsilon ij is equals to ek dkij. This is the inverse piezoelectric effect, where the coupling strain of the material to an external electric field is related by this, where epsilon is the strain tensor, this is the strain tensor, and E is the electric field vector. Both effects can be measured. So going back to the phenomena of ferroelectricity, okay, uh, we are concerned with the macroscopic description of ferroelectrics, that is the study of the electrical polarization on length scales much longer than the separation between the atoms. On this scale, the polarization of a solid can be regarded as a continuous degree of freedom. And in this view, enable us to understand the onset of ferroelectricity as a phase transition like any other to discuss the types of phase transition and to begin the issues of domains, switching and hysteresis. So one thing is can be described by domain theory, right? Ferroelectric switching, and finally the hysteresis. So what is ferroelectric and the macroscopic description of the origin of ferroelectricity is the material that poses a permanent electric dipole and can start looking at the small molecules. A molecule that is symmetric, such as methane, has no dipole, but many simple molecules that are not symmetric, like H2O, and have a dipole moment which is a non-zero value. So in the further steps, we have discussed when a transition from the paraelectric to ferroelectric phase takes place, it is accompanied by the appearance of spontaneous polarization. In principle, two interactions should occur in this transition. One is work done in polarizing the medium, and the second one is the attractive dipole-dipole interactions. In order that the process be spontaneous, the lowering in energy in attractive dipole-dipole interaction should be more than the energy absorbed in the polarizing the medium. So let us suppose that the work done during the process of polarizing the medium is W1 is equals to integration F dx, where F is the force and dx is the macroscopic electric field. Then the polarizability is given by alpha is equals to P upon E, which turns out to be this one. Alpha is equals to P upon E, where this P is the dipole moment is E times X, and E is simply force per unit charge. Therefore, W1 is equals to integration F dx. If we put the value of F here, so it is E square x square divided by twice alpha, that is P square by twice alpha. And further, the attraction energy due to the dipole-dipole interactions will be W2 is equals to minus P square upon R cube, where the negative sign indicates that it is attractive force and R is the distance between the dipoles. If W1 is equals to modulus of W2, so we find this alpha is R cube by 2. So for an isotropic system, that is for cubic dielectric, this equation W1 is equals to P square upon twice summation Ni alpha I, where P is the polarization and Ni and alpha I are the atomic concentration and the polarizability of the ith atom respectively. In order to calculate W2, the local field at the atomic site in the dielectric is given by this equation, E local is equals to E plus P upon 3 epsilon naught. For spontaneous polarization, this E must be 0. Therefore, E local is equals to P by 3 epsilon naught. If we put this E here, then W2 is equals to minus E local dp, that is minus 3 epsilon naught integration P dp, which is minus P square by 6 epsilon naught. If we equate W1 is equals to mod W2 here in this case of isotropic systems, this turns out to be 1 by 3 epsilon naught summation Ni alpha is equals to 1. Again, for an isotropic system, the Clausius-Mosotty equation can be written in terms of this equation. And if this equation have to satisfied, then the dielectric constant becomes infinity or infinite. In practice, although the dielectric constant does become very high at the order of 10 to the power 3 to 10 to the power 5, in many cases it never becomes infinity. Therefore, let us put this is a small value delta, which is uh, mm, which can be subtracted from 1, where delta is far lesser than 1, and the dielectric constant becomes epsilon is equals to 3 minus 2 delta over delta, which approximates as 3 over delta. So now if near the critical temperature Tc, the deviation delta varies with the temperature in a linear fashion according to delta is equals to 3 upon C T minus Tc, where C is the Curie constant, and this equation becomes epsilon r is equals to C upon T minus Tc. This indicates that the dielectric constant follows the Curie-Weiss law, and this figure shows the dependence of the dielectric constant with temperature in a ferroelectric crystal, followed by a para-ferro transition at the Curie temperature. So this is the phase transition over T, and this is the dielectric behavior where this real part of dielectric constant shows a large divergence at near critical temperature. So the ferroelectric that consists of ionic crystals with crystal structures closely related to the perovskite like AbO3 and perovskite structures. The perovskite structure is the simplest crystal structure, as you can see from this. This is a typical BaTiO3 structure. It is cubic and barium 2 plus ions at the cube corners, oxygen 2 minus ions at the face centers, here, here, and titanium 4 plus ions at the body center. So below a Curie temperature, the structure is slightly deformed with respect to the cubic structure shown in this case. So this structure exhibits ferroelectricity. The perovskite applies to the minerals such as calcium titanate, ferric titanate as well. So we consider first the magnitude of the ferroelectric effects in barium titanate. We suppose that the Curie point is determined approximately by the interaction energy of a dipole with the local internal electric field caused by the polarization itself. So the interaction energy is minus half E dot E, where E will be of the order of minus PS. and the interaction energy is the order of 10 to the power minus 13 arg. To obtain approximately the transition temperature KTC, where Tc is 1400 degree K, and observed, it is a calculated value and actually observed for barium titanate at the order of 380 degree K. So this is the spontaneous polarization of barium titanate as a function of temperature, and the discontinuity is near here. Okay, the temperature range is not shown. Anyhow, the discontinuity is near 0 degree and minus 80 degree are caused by the small changes in the crystal structure. The indication of the ferroelectricity in barium titanate is provided by the hysteresis loops and is observed at temperature below the transition temperature, that is 107 degree. At temperature above the transition, the loop reduces to a straight line and the spontaneous polarization as a function of temperature is being shown here. The dielectric constant is usually very much larger than the measured perpendicular to the c-axis than when measured parallel to it. Basically, this is the basic perovskite structure of barium titanate, the unit cell of barium titanate. And as we lowered the temperature, this barium titanate exhibits a first phase transition cubic to tetragonal at about 120 degree, then tetragonal to orthorhombic at about 0 degree, then tetragonal to orthorhombic, and followed by rhombohedral transition closely at minus 90 degrees centigrade. So these are the temperature versus dielectric phase transition plot when my symmetry in the crystal are being reduced over temperature. The same barium titanate in different cubic and hexagonal forms. These are the typical table where you can see the transition temperature as well as the remanent polarization for different materials. Particularly for KDP, it is around much lower than the room temperature, but barium titanate is well above the room temperature, and the remanent polarization is quite high at the tetragonal phase. PZT is another most familiar ferroelectric material, and this stoichiometric ratio decides a key factor in the Curie temperature, and observed polarization value is at the order of 10 microcool Curie per centimeter inverse. So these are the typical table of substances which shows ferroelectricity. This is another important plots where real part of dielectric constant are being plotted with temperature, and with the same phenomena, the paraferro transition are being portrayed in the ferroelectric hysteresis loop. So this part beyond Tc are my most random phase, and below Tc is the more ordered phase where the ferroelectricity is being exhibited, and the same kind of phenomena are being plotted in the P hysteresis loop. This PS is corresponding to peak in the dielectric here, and the same is being observed. The minus EC and DC are given by a hump in the electric field versus dielectric constant behavior. So this part is for ferroelectricity, and beyond TC, this is a linear dependence of P versus E, where the paraelectric phase are being portrayed, and up to a certain limit, this P is proportional to E, and that's why these materials are called linear dielectrics. Ferroelectricity, as I mentioned, the nonlinear behavior of the dielectrics, and for particular paraelectric phase where my P is proportional to E, the dielectric constant gives a hump at about origin, but here the hump not shows any peak at the origin, but at EC and at minus EC. This peak are being observed. So the properties of the ferroelectrics can be understood by reference to the fictitious one-dimensional crystal made up of two atoms of oppositely charged as shown in this figure. In this crystal, it is clear that we can orient the dipoles to point all to the right or to the left. The two structures are completely equivalent except that they have an opposite sign to the dipole moment. They must therefore have exactly the same energy. We could transform one into the other by dragging one type of atom toward the other. As we do so, the bulk polarization will reduce in magnitude and change sign as the point where the atoms are equally spaced and finally switch to the opposite direction. So given that we know the crystal is stable in either of the two polarized states, there must be an energy barrier between the two states. And we can sketch the curve for the energy as a function of polarization like this, where we switch between the two states. In an electric field E, the two stable states no longer have the same energy because of the electric polarization energy minus P dot E, right? The wells are tilted by the electric field. So it is also clear from this figure that a small field will not necessarily immediately switch the polarization from one direction to the other because there is a barrier to overcome, right? This is the barrier. So in an ideal case where all the dipoles have to be overturned together, there will now be hysteresis, which I can show in this figure. So while this figure demonstrates the origins of the hysteresis phenomena seen in a real ferroelectric, so it is much too simple a description because of a real material not all the microscopic dipoles will uniformly switch together. So this description is limited to low temperature. It is common to observe that as the temperature is raised, the bulk polarization decreases and vanishes abruptly at a temperature Tc. So this is the phase transition, just as in a ferromagnet raised above its Curie temperature or a solid raised above its melting point. So it arises microscopically because as temperature is raised, the thermal vibrations of the molecule in the solid cause fluctuations which overcome the potential barrier between the two wells. So it is most easily understood in a molecular crystal such as NaNO2, where one can imagine that one molecule can fluctuate between two configurations, each of which has a double potential like this, and some interactions between the dipoles that tend to align them, right? So the microscopic theory of how this happens will be different from the material to material, but the macroscopic properties of the phase transition will be similar across many different classes of materials. Okay, so this macroscopic theory provides a very useful description of many different ferroelectrics. This is the Landau theory of phase transition. So any crystal is in thermodynamic equilibrium state that can be completely specified by the value of the numbers of variables. For example, temperature T, entropy S, electric field E, polarization P, stress sigma, and strain S, right? So this can also be explained in the light of the domains. So in the domain theory, we have pretended that the polarization in a ferroelectric can be treated as entirely uniform, and this is far from the case. There are many reasons for the existence of domains, including non-uniform strain, microscopic defects, and the thermal and electrical history of the sample. But even in an ideal crystal, domains are to be expected for energetic reasons. The macroscopic bulk polarization is produced by a displacement of a positive charge relative to negative charge at the surface of the sample. There must be a net charge density of opposite signs on the opposite sides of a crystal. In a simple manner, it can be plotted like this. If this is my negative charge and this is my positive charge regions, outward normal, outward normal, and the polarization projects in this direction, right? So this is a surface charge density generated by a bulk polarization at an interface. So the macroscopic bulk polarization is produced by the displacement of the positive charge relative to the negative charge, and the charge density of oppositely charged ions. With a little geometry, the surface charge density per unit area can be written as sigma equals to P dot n, where n is the vector normal to the boundary. So these surface charges themselves now generate electric fields, both internal and external, to the sample, and the fields themselves store energy just as in capacitor. The system will minimize its energy by abolishing, as far as is possible, the surface charges, and in a thin film, for example, this makes clear that the preferred orientation of the polarization will be lying down in the plane of the film rather than the pointing perpendicular to the film. So if one has crystal that is thick in all dimensions, another situation is preferable to introduce the domains where the polarization is oriented to be always parallel to the crystal surface. Such a situation can of course only be achieved by introducing domain walls into the bulk, and this will produce a polarization charges unless the walls are appropriately oriented. The interface charge density between the two neighboring domains is, okay, let me draw the domain structure first. These are my domains. And this can be oriented in a different manner like this. This, 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 this. So this is the ideal domain configuration in a single crystal of a cubic ferroelectric material, where the coupling to strain is negligible. On the right is the configuration adapted when strain effects are important. So the interface charge density between two neighboring domains is sigma is equals to P1 minus P2 dot n, where P1, P2 are the polarizations of the two domains and n is a unit vector normal to the interface. The two cases when the surface charge will exactly vanish are when the polarizations are anti-parallel to each other and parallel to the domain wall, called the 180-degree domain wall, or when the domain wall bisects the angle between two domains pointing head to tail. Because we are often dealing with nearly cubic crystals, there are possible polarizations are at 90 degree to each other. The latter is often termed 90-degree domain wall. So both these type of walls are illustrated in this sketch, where it is the ideal configuration of the polarization in a pair of ferroelectric single crystal, and which bears obvious comparison to the ideal magnetic configuration in a single crystal bar magnet that may be familiar to some. The presence of domain walls involves other energy costs. Firstly, the domain wall is microscopically different from the bulk, and the energy gain is forming the polarized ground state has been lost. Secondly, the polarization is coupled to elastic strain, as we saw above, and we must also make sure that the strain fields are compatible. There is no difficulty with a 180-degree domain wall, but a 90-degree domain wall produces problems, and the ideal configuration is by no means ideal in terms of the strain fields. The existence of domains in a sample automatically generates inhomogeneities in the strain which interact in complex ways. So there is another feature of ferroelectric domain walls which is not shared by magnetic domains. As far as we are aware, magnetic monopoles do not exist, and therefore the magnetic charges that are generated on the magnetic boundaries cannot be screened. In ferroelectrics, the surface polarization charges can be and are screened by real electrical charges from impurities, defects, and migrating ions from for example, the motion of charged species to domain walls then provides a mechanism for memory, imprinting, and fatigue, topics which will recur in the practical senses. So domains, their motion, pinning, and switching are fascinating phenomena in their own right, and the complexities of domain motion in practical materials are at the heart of understanding device performance. So the brief and the idealized discussion above is only the most superficial of introductions to the topic of domains in the light of ferroelectricity. So in a ferroelectric crystal, it is likely that the alignment of dipoles in one of the polar directions extends only over a region of the crystal, and there can be different regions in the crystal with aligned dipoles which are oriented in many different directions with respect to one another. So regions of uniformly polarization are called domains, separated by a boundary called domain wall. This is the domain wall. These are the domains. So one should not confuse ferroelectric domain walls with the grain boundaries. Depending upon the grain size, one grain can have more than one or more domains. So the type of domain walls that can occur in a ferroelectric crystal depends upon the crystal structure and symmetry of both paraelectric and ferroelectric phases. For instance, rhombohedral case of lead zirconium titanate EZT has PS vector along 111 direction, which gives the 8 possible directions of spontaneous polarization with 180 degree, 71 degree, 109 degree domain walls. On the other hand, a tetragonal perovskite structure, lead titanate PbTiO3, has PS along 001 axis, and here domain walls are either 180 degree or 90 degree domain walls. So this is the schematic presentation of 180 degree and 90 degree domain walls in a tetragonal perovskite crystal such as PaTiO3. And formation of the domains may also be the result of the mechanical constraints associated with the stresses created by the ferroelectric phase transition, that is from cubic paraelectric phase to tetragonal paraelectric phase in lead titanate. Both 180 degree and 90 degree domains minimize the energy association with the depolarizing field, but elastic energy is minimized only by the formation of 90 degree domains. Combination of both effects lead to a complex domain structure in the material with both 90 degree and 180 degree domain walls. So the next question is, why is there a domain wall? So the main driving force for the formation of domain walls is the minimization of the electrostatic energy of depolarizing field ED due to the surface charges due to polarization and the elastic energy associated with the mechanical constraints arising due to the ferroelectric to paraelectric phase transition. The electrostatic energy associated with the depolarizing field can be minimized by splitting of material into oppositely oriented domains or compensation of the electrical charge via electrical conduction through the crystal. That's why application of an electric field to a ferroelectric ceramic leads to the alignment of antiparallel or off-aligned dipoles to reorient themselves along the field. And this is the typical TEM image where you can see the domains in the BTL3 crystal. This is the ferroelectric switching and the domains which are being characterized in the hysteresis loop of a ferroelectric material. So finally, I conclude the ferroelectricity by saying that the increase in the field strength forces the growth of favorably oriented domains in the expense of oppositely oriented domains, and polarization starts increasing rapidly until all the domains are aligned in the direction of the electric field, that is, reach a single domain state. And polarization saturates to a value called the saturation polarization. The domain's reversal actually takes place by formation of new favorably oriented domains at the expense of the unfavorable domains. Now, when the field is decreased, the polarization generally does not return to zero, but follows some other path, and at zero field, some of the domains will remain aligned in the positive direction, and the crystal exhibits a remnant polarization.
To bring the crystal back to zero polarization state, a negative electric field is required, which is also called the coercive field. So further increase in the electric field in the opposite direction will cause complete reversal of the orientation.